Okay, so basically last time we ended up with the concept of gravitational potential. That was the last topic from the chapter of uh, gravitational forces, right? Or the gravitational field. And today we are going to start with the concept of ideal gases. And in ideal gases, we have to know about some basics of gases, just like you know that we need to measure a gas in a mole. The basic, very basic concept you also used to write in chemistry also, that amount of substance can be calculated in moles, right? So that's a unit of amount of substance is mole. So in gases, we are going to work in moles. Then there is Avogadro number, that is a constant value, right? So these are basic
Yes,
things. We are not going to discuss that because that is the basic, and during calculation on during different concept, we just revise that concept. Otherwise, you are already studying that concept in chemistry, right? So basically,
yes,
we are going to start with the concept of ideal gases. And in ideal gases, you know that there are different laws that we studied in IGCSE also, just like the Boyle's law and the Charles law. In Boyle's law, we discussed that pressure is inversely proportional to volume if temperature is constant. And if we take Charles' law, so pressure is directly proportional to the temperature if volume is constant. So all these things we are going to combine together, and we discuss all the concepts, right? Any confusion in Boyle's law previously? If I just write the
no,
form, because you know we used to write in IGCSE also P1 V1 is equals to P2 V2, like the same equation from the Boyle's law, right?
yes,
So basically there are two equations. This is for Boyle's law for initial and final state, and for Charles' law P1 over T1 is equals to P2 over T2, right? So this is the basic equation that we used to write for uh, the Boyle's law and the Charles law that we already discussed in IGCSE level, right? Basically, we need to start with the concept of ideal gases, and there are different derivations in this chapter. We need to discuss about that also, right? And there are some assumptions, because in states of matter we already know about the thing that in air, in gases, air molecules are far away from each other, the intermolecular forces are weak in gases as compared to solid and liquid, all these concepts, right? And if you know about the concept of ideal gas equation, so the ideal gas equation is PV is equals to nRT, right? So the concept of PV is equals to nRT is P represents pressure, V represents volume, N represents number of moles. What about R? This is journal
it's
gas.
constant value.
Yes. And T is temperature. So this is the journal gas equation that help us to solve numericals uh, in our syllabus. And we can also write this equation in different form. And the second form of this ideal gas equation is PV is equals to NKT, right? Now P and V remains the same pressure volume, but this capital N is small is number of moles, capital N represents number of molecules, and K represents again constant. This time it is known as Boltzmann constant, and the value of Boltzmann constant is 1.38 exponent minus 23 joules per Kelvin, right? And T represents same temperature. Okay, so we use these two equations to solve multiple problems related to the gases, right? And basically, if we talk about the Boltzmann constant, so because this is the new quantity that we discussed today, and the Boltzmann constant is you already identify that Boltzmann constant can be represented by the K, and the definition of Boltzmann constant is we can easily identify the Boltzmann constant with the help of internal gas constant divided by Avogadro number, right? This Na represents Avogadro number. That is also a constant value. This is Avogadro's number and R is gas constant. You know that both values are constant. The value of R is equals to 8.31 at standard temperature and pressure. And the value of Avogadro number also remains same, 6.02, 23. And dividing these value give you the same result, right? You can also calculate by the calculator, you will get the same result, right? Basically, why we are using the Boltzmann constant, that is the question. So basically, we are using the Boltzmann constant to study the microscopic properties, right? So basically, when we are going to talk about some detailed or the base or the microscopic properties of different particles like kinetic energy of molecules, because normally what we observe in our daily life, the temperature, right? Like if we start providing thermal energy to water or gas, so generally what we use word, we use temperature is increasing, right? But if we want to discuss about the base of that temperature, that what is the reason or what is the science behind increasing temperature, so the science behind increasing temperature is known as that the internal energy or the kinetic energy is increasing, right? So that is the concept of microscopic property, right? Any confusion? No. Kinetic energy, potential energy, total energy. So this type of concepts when we are talking about, so we use Boltzmann constant. And if we are using macroscopic like temperature, right? If we are talking about temperature, so we can easily use the ideal gas PV is equals to nRT. So that is also usable, right? And if we are talking about a minor change in internal energy like kinetic potential or total energy, so then we use the concept of the Boltzmann, right? And secondly, if we talk about some other concept in this chapter, so the next very important concept and very easy concept, that concept is related to assumptions of kinetic theory of gases, right? Because we have to study all detailed about the molecules of gases. So before starting that, we have to make some assumptions, right? Because we know that molecules are not visible or cannot be observed by our normal eye. So that's why it is very much important to have some assumptions or some basics of kinetic theory of gases, right? Just like in solid and liquid are easily visible, but still the molecules of liquid are not visible. So that is the microscopic property. If we are talking about the surface of water, behavior of the water, so that is macroscopic property. Okay. So there are some assumptions. Let's suppose the very first assumption is that gas consists of or gas contains atoms and molecules that are randomly moving at high speeds, right? So gas contains atoms and molecules randomly moving at high speeds, right? So this is the basic concept that we need to know about it, because already we know that they are in random motion because there is no fixed shape, no fixed volume. So that's why they are in random motion moving with high speeds. And the second thing is that kinetic energy is directly proportional to the temperature, right? Because if we increase the temperature, so you observe that in water, the water molecules or the surface of the water converts into the bubble and then into steam, right? So basically, increasing the temperature will increase the kinetic energy, right? So there is a direct relation. So second point is kinetic energy is directly proportional to the temperature. If we increase the temperature, so kinetic energy will also increase, right? Again, temperature is macroscopic constant concept. Kinetic energy is microscopic concept, right? And the third thing that we need to know, that there will be elastic collision in gas molecules, right? Why elastic collision? Any idea?
Um, Elastically, because particles are constantly moving high
Okay.
speeds.
Okay. Basically, normally what we observe that if we take example of the snooker ball, so when one ball strike with the other one, so that is a very rigid and very hard solid object, right? And if we just compare with the tennis ball, so when two tennis ball collides, so they will bounce back with more energy as compared to that solid snooker balls, right? So basically, that solid ball when they collide with each other, so that is inelastic collision. And when football or tennis ball collides with each other, so that is elastic collision. So the main purpose of elastic collision or using the concept of elastic collision is that in elastic collision, energy and momentum remains conserved, right?
Yes.
Because if these quantities remains conserved, so it is very easy to understand and to drive the concept, right? If there are multiple variations, so it will be like very advanced concept, right? You just need to solve each and everything, each and every detail related to that concept. So that's why we consider that gas is in elastic collision, right? That's why we observe that the oxygen molecules in our atmosphere remains at the same level, because if they are losing energy in form of heat or some other concept, so day by day your level of oxygen gas from the ground is going to be decreased day by day, right? Because it is losing energy, and after some time all molecules are on the ground level, right? So that's why we consider that all collision of the gases are elastic, right?
Yes.
And there are some other concepts, because in exam they used to ask sometime that write three important points or write in terms of kinetic molecular theory, uh, what are the concepts or what are the assumptions for molecules of gas. And the next thing is, if we talk about the volume of molecules, if we talk about the volume of single molecule, or if we talk about volume of molecules, so the volume of molecule is negligible as compared to the volume of the container, right? Because you can see that we can easily fill a high, or we can fill gas with high pressure into the cylinder, right? So the volume of cylinder is very much greater as compared to the volume of molecules, right? Because we know that there are multiple molecules filled in a single cylinder. Okay. So the volume of molecule is negligible to the volume of container. Like if we fill water in 500 ml bottle, so you know that volume of that bottle is very much large as compared to the volume of one molecule or multiple molecules, right?
Yes.
And further, if we talk about their time of collision, so we can say that because they are continuously colliding with each other, so we can say that the time of collision, so basically the time of collision is again negligible as compared to the time between collision, right? Because they are moving with very fast speed, and when they are moving with very high speed, so their collision will be in very short time interval, right? And
Yes.
next point is there are no forces of attraction or repulsion between molecules, right? No force of attraction and repulsion between molecules, right? The solid bodies, we discuss about the concept of gravitation. So in gravitation we observe that there is a force of attraction between the planets, but in this concept there is no such concept, right? And next thing is the molecules are in random continuous motion. Okay, so these are some concepts, right? And I will also share this file with you, so you just need to remember these points. It will help you to write in your answer, right?
Yes. Yep.
Clear? Any confusion?
No.
Okay. Okay, now there is a concept of, okay, this derivation is very much important because they will ask you to drive the derivation. So basically this derivation is related to the pressure, right? That in pressure in the gas molecules is equals to 1 times 3 the density of the molecules, right? So basically we need to drive the equation like the derivation is related to pressure is 1 over 3 times the density into mean square speed. I will also explain that what is the concept of this c square, right, after driving the equation. Because if we start talking about this root mean speed individually, so that will be a lengthy one. So we will discuss during the derivation, right? So let's suppose if we start the derivation. So for considering the derivation, we start with the concept of a cube. So let's suppose if we consider a cube, right? And in cube, we consider single molecule. So you know that this molecule will move in random direction and with random motion, right? Okay. So you can see that this molecule will move in random motion. It will collide with multiple time with multiple walls, and it will bounce back, and it will strike with some different momentum, then repel back. We know that we are using of elastic collision. So due to that elastic collision, momentum remains conserved, right? So let's suppose if we start the derivation like this, that let's suppose if molecule move in forward direction, let's suppose if molecule strike with the wall in forward direction, so it will also bounce back, right? So once it will move in forward direction, then it will bounce back in the same opposite direction. Okay.
Yes.
So the momentum will be equals to, normally momentum is equals to mv, right? But this time we are taking speed as c. Okay. So your forward momentum is, let's suppose, positive. Your backward momentum will be with negative sign, because we know that in the concept of momentum you already studied that due to change in direction, your momentum has contains negative sign because of opposite direction. Okay. So basically we start the derivation from this concept that the change in momentum will be equals to final momentum minus initial momentum, right? Positive is the initial, and this negative will be the final. Clear? Any confusion?
No.
So basically your momentum is going to be combined over here, but with only negative sign. Okay. Clear? Any confusion? So this is the first
No.
we got the concept like this: when molecules move in the forward direction and it will collide back. So due to that collision, we got the negative sign because of the opposite direction. And after the collision, our final momentum will be equals to this equation. So this is our equation number one. And the next thing is that we need to count the number of collision in 1 second, right? So your second concept will be like this: you need to calculate the time. So if you want to calculate the time, so your time will be equals to the distance. So basically distance will be twice of the length, because we are moving in forward direction and in backward direction. So your length is going to be multiplied by 2 times, right? And the formula for the speed is equals to distance upon time, right? And if we just shuffle the value, so your time will be equals to distance upon speed. Clear? Any confusion? If we just replace speed with time, so you can see that this will be normal formula: speed is equals to distance upon time. Okay.
Yes.
And we are using c for speed. I will explain that because that is the concept of root mean square speed, right? So this is the formula for time. So this is the second equation, okay?
Okay.
And the third thing that we need to discuss is related to the change in momentum, right? Because you know that in the topic of momentum, we also studied that force is equals to rate of change of momentum, okay?
Okay.
So force is equals to rate of change of momentum, okay? Delta p over delta t. Now we already have value of change in momentum. So change in momentum is equals to 2mc. We are just ignoring minus sign because we know minus sign is only for direction. We are not calculating direction right now. So we just take 2mc, okay?
Okay.
And the value of delta t is 2l over c. Combining the values, so what will you get in final answer? Your force will be equals to value will be flip over there and c will multiply with c to cancel out each other. So force will be equals to mc square over l. Clear? So this is the
Okay.
value of force.
Yes.
Now we know that when force is going to be applied on any surface, so there will be a concept of pressure. Pressure is equals to force per unit area, right? So the next step is related to the pressure. So the value of force is already calculated. And if we want to write the value for area, so what do you think that what will be the value of area? In area, we need to choose two length, right? Square of the length, like meter square, centimeter square. So the area will be equals to length square. Okay, clear?
Yes.
Square of the length. So finally, what will be your final equation for pressure? Right? Because mc square over l means we again flip the values l square over 1. So you will get the value l square will multiply with l. So you will get mc square over l cube. Okay, clear?
Okay. Yes.
Because in this situation, we write the concept. This is the value of time. So we need to flip both values 2l over c. But in this concept, we are only taking the value of l square and there is nothing in the denominator. So l square over 1, when we flip the value, so we will write 1 over l square, right? Because this is the complete value of force, right?
Yes.
This is like mathematical concept. Okay, so till now we got the value of the pressure. And if you remember that previously we discussed that uh, we are only talking about only one concept, that is only one molecule, right? Let's suppose if we talk about the momentum of all molecules, right? So what we need to do, we just need to multiply capital N, right? Because we are only talking about one molecule right now. From the diagram you can see we start from the concept of one molecule. Let's suppose if we talk about n number of molecules, because we don't know how many molecules are there. So there are n number of molecules, right? So basically your final formula will be equals to nmc square lq, right? Clear?
Yes. Yes.
And we need to convert this. So basically the concept of this value that is written with symbols, with brackets, with c square. So basically this is known as root mean square speed, right? Root mean square speed, right? So basically when we are talking about ideal gas equation, so it includes root mean square. Root mean square means we have to take the average speed of the gas particles, right? Because and we know that again the concept that direction will be anywhere in 3D form, because we have 3D shape, 3D concept. So there is a concept of volume. So to find out the direction or to calculate the speed, we just take the vector, we just take the direction, because once particle is going to move in forward direction, so it will also bounce back in backward direction. So that's why we take the concept of square and root, right? Square mean or root mean square speed. Okay, so that
Yes.
is the concept. So basically if we take a normal speed, so that is only in one direction, but we are taking a collision concept over there. So that's why we are taking root mean square speed, right?
Yes.
Now we are having equation number 4. Now till as we discussed that we are talking about the 3D. So let's suppose this speed is only for one axis, and if we consider all three axes, so we need to write for three axes, right? For x-axis, y-axis, and z-axis, right? So basically we can say that this root mean square speed is the sum of speed in x-axis, in y-axis, and z-axis, right? Clear?
Yes.
And you can see that since we are taking, or if we consider that in all direction, we know that there is elastic collision, so speed in all direction remains same, right? So this will be equals to, let's suppose if we consider only x-axis, so the speed in x-axis will also remain same for y-axis and z-axis, right? Getting the concept?
Yes.
If we take any particular direction, so in all direction you will get the same speed. So we can say that we can write this equation like this, right? The speed in x remains same for y and z also. So we just take any one axis and solve for one axis, or we take the reference of one axis and it will remain same for all the axes. So it means your speed or root mean square speed will combine. Okay, it will be equals to 3 times cx square, right? Let's suppose if we are talking about only x axis. Okay,
Okay.
any confusion?
No.
Basically this derivation is slightly lengthy, but I try to minimize in simple form. That's a step by step situation, so you will get the concept one by one, that we started from which point and we are ending at what point. So that is the concept. And after that, so we ended till c square is equals to cx square plus cx square plus cx square. Combining the equation will give you the concept like this: 3cx square, right? Or we can also write this equation like this. Okay.
Yes.
So basically your value will be equals to So your value will be equals to 1 over 3 times the root mean square speed, right? And now we can substitute this value in our equation number 4. So your equation number 4 will be equals to, so your equation number 4 will be equals to, on left hand side we are having p, and we know that this length is now length q, and we can also replace it with the concept of volume, right? Because 3 length means volume, so this will become volume, right?
Yes.
So equation will be equals to PV on the left side, because P is already on the left, and we just multiply this length on the left side. So it will be equals to PV is equals to NM, and substituting the value of the speed will give you the concept like 1 over 3 root mean square speed, right? So this is the concept. And finally, final equation, right? So this is our equation till now. Okay. And from which point starting? We started from P is equals to 1 over 3 density C squared, right? So basically, if we just take the reference from this equation, and if we shift, because we know that formula for density is mass per unit volume. Okay. So if we write equation like this, so we know that M over V is equals to density. So final equation will be P is equals to 1 over 3 density and C square, right? Or we just
Yes.
include this N with the density symbol, because we are talking about N number of molecules, right? So this N will multiply with M. Okay. So because if we are talking about only one molecule, one object, so we write M over V. But we have multiple molecules, so N M over V will give you the concept of density. So this whole value gives you the concept of density. Because you know that capital N is only a number. It is not a physical quantity, it is only a number. So your final equation is derived like the same as we discussed, that we have to derive this equation, right? So your pressure is equals to 1 time density of density into the root mean square speed. Okay.
Okay.
So any confusion?
No.
And just one more short derivation, and after that we will end for today only, because this is like a typical concept. And and in assumption, you remember we discussed that kinetic is directly proportional to temperature, right? So sometimes they used to ask their drive, or with the help of derivation, or in terms of kinetic energy and temperature, prove this relation or drive this equation. So let's suppose if they ask you to drive the equation that kinetic energy is directly proportional to the temperature, so how we are going to drive this equation? So we start from journal gas equation, and the journal gas equation is PV is equals to NKT. So this is the first equation. And the second thing is, we need to take the reference from the equation that we drive. PV is equals to right? So we take reference from this equation. This is equation number 2. And on left hand side, we know that PV is same in both equation. So if we compare the equation, so comparing the equation will give you the result NKT, right? Because left side of both equations are same. So we can easily compare their value by writing one value on left hand side and one value on right hand side. Okay, clear?
Yes.
And you know that n on both sides will cancel out. So your final equation will be equals to like this. Okay. And if you
Okay.
remember that half mv square is equals to kinetic energy, right? The formula of kinetic energy is half mv square because we need to drive for kinetic energy. So we need value for kinetic energy, right? So what we need to do, we just multiply and divide two uh, with the equation. So you will get the same idea. So what we need to do, we just need to do additional step. So let's suppose if we multiply and divide, because we know if we want to multiply some additional value, so we also need to divide that one. So that will uh, remains the effect of the equation remains same. So if we multiply and divide by 2, so what you got, you just need to shift this value 3 kT on the other side. 3 kT like this. Okay. 1 2 remains over here, and the second one that is multiplied over here in denominator, and this 3 will shift in numerator. Okay. And now you can see that
Okay.
half mc square gives you the concept of the kinetic energy, and this 3k over 2 is constant. So in simple words, we can say that kinetic energy is directly proportional to temperature. And if we just replace this constant directly proportional sign, so that can be replaced by this constant value. Okay. Because we know that k is Boltzmann constant, 3 over 2 is just simply a number. So you will get the same derivation, that is half mv square is equals to kinetic energy, and 3 over 2 is constant, and k is the Boltzmann constant, right? Clear? Any confusion?